Hello, everyone. Welcome to the second part of the Opolis talks. This is this is Athanase Papadopoulos, who's going to tell us about Thurston Lipschitz Maps, Thurston Lipschitz Maps.
Okay, thank you very much. I want to thank the audience also, and I'm very happy to see familiar faces. I gave a talk of, I gave several courses this year in Bombay, in Varanasi, and talks at the IFR and so on. I know almost all the students here and the postdocs. So I will talk about something which I did not talk about, something very simple, in fact. And this is the Euclidean case of Thurston's best Lipschitz map. And there are a few papers, in fact, which I want to give the names of my co-authors because I would not, maybe I would not say them later. So there's Ismail Saglan. So this is a Turkish postdoc who came to Strasbourg. In fact, I worked with him on this subject. And then there's Kenichi Ohshika and Hideki Miyachi. And there are, so this is, these are works which we did on like 2020, 2025. So the papers are published starting 2023, 24. And then there's a work on this I did around 2005. So this is with a student of mine at that time. And a colleague, Mark Troyanov. So, okay, so this is the things which I will say are joint with several people. And there are several cases, in fact, which we considered. Some of them are very natural. And the first case is Lipschitz Maps. Well, best Lipschitz Maps between Euclidean triangles. So, as you know, Thurston's theory is a hyperbolic theory, best Lipschitz maps between hyperbolic surfaces. The building block is a Lipschitz map. A Lipschitz map between ideal triangles. So there's a canonical construction of a foliation of the ideal triangle by pieces of horocycles. And you take two such ideal triangles. So they are marked. You can think of them as the same ideal triangle and whatever. This central region is sent to this central region, and then and then a piece of horocycle at length at distance k from this central region is sent to a piece of horocycle at distance, say, let's see, Lk, well, L is greater or equal to 1, and then you have two surfaces, two hyperbolic surfaces, and then the generic case is a decomposition into ideal triangles, whatever, with these pieces of horocycles. And then you combine these maps between the horocycles. And you get Thurston's map. So it's based on in fact, it's very simple idea, decomposing the surface into. So now what I want to consider is, so I said the Euclidean case. So my space is, well, space of surfaces equipped with the Euclidean structure. And the most basic case is I take T. T stands for Teichmüller space. This is space of triangles in the plane, so Euclidean triangles. And I want to put a metric here, and I want to put a Finsler metric. I want to imitate what Thurston is doing. I want to find the geodesics for this metric. I want to see whether this metric is hyperbolic or not, or okay. So all the properties which I know for the Teichmüller space of hyperbolic surfaces, I want to ask the same questions here. So for this, okay, I gave the names there. I don't need to tell you who did what. So first of all, you have this question of best Lipschitz map between a Euclidean triangle and another Euclidean triangle. So it's natural, in fact, to normalize and to take the triangles of area A. Otherwise, I get things which I want, which I don't want, and so this second triangle would be like that, same area. And what is a best Lipschitz map, or the best Lipschitz map? Of course, the first guess is to yeah. Let me say also these are marked triangle. I have a marking, like marked surfaces there. So the marking here is just a cyclic order of choice of the vertices in the positive direction. Not a cyclic order, but a choice of the vertices with the right cyclic order. And then, what is the best Lipschitz map? The first guess is that this is the affine map, right? You would expect this, but it is not, in fact. The best Lipschitz map is more complicated than the affine map. I let you think a little bit or read one of our papers. And then the next thing, okay, so let me tell you the idea, in fact. The best Lipschitz map between right triangles is the affine map. And when you have two triangles which are not right triangles, then you have to compose the two affine maps. This is the answer. Another thing is that when you start to develop this theory, it turns out that the case of acute triangles is much easier than the general case. There are things which we proved for acute triangles, which we don't know how to prove for general triangles. So this is, I want to put here space of acute triangles. Okay, so we want to follow the Thurston outline. So I don't think I have to recall what is the best Lipschitz map. Let's say that we have this L. So here, yes, I want to put acute. I have a map. This is my distance function between, the first thing I want to prove that this is equal to something else, like in Thurston's case, where he proves that the distance obtained by best Lipschitz maps is the distance obtained by comparing the length spectrum, right? So here I have another map. And well, what is the length spectrum here? I want to compare the length of edges, right? And then it turns out that this is not sufficient. So I take the length of the altitudes. 1, 2, 3. I have the corresponding altitude here. And then, so this is well, the log of the supremum of the, so if this is, the lengths are A, B, C, and A prime, B prime, C prime, and then the altitudes H, H, I, J, and so on. So length of A prime, A prime, A, B prime, B, length of C prime, C, and then so on, H prime, H. This is my comparison of the length spectrum, and the first result, let's put it here, position 1, K equals L. This is one analog of the Thurston theorem, which says that the distance obtained by taking the best Lipschitz constant is equal to the distance obtained by comparing the length spectrum. Yes? Okay, and then you ask about, let's put it here. So let me put this as proposition 2. In fact, this distance is symmetric. Unlike Thurston's distance, this distance is symmetric. And okay, now I want to describe the geodesics. This distance is symmetric, in fact, because okay, I don't want to this. The geodesics. So now I look. There's a description of the geodesics. So G of T, a path in this space. It's a family of triangles, and I want to consider the angles. With angles, yeah, I should have chosen other notation. Okay, let's. What do I choose for angles? I want to take theta 1, theta 2, theta 3. Okay, let's take this. Even though I started there with so these are the angles at the vertices. Of course, the vertices are marked vertices. So and well, okay. With these theta 1, theta 2, theta 3, say in some interval AB, and such that not all of them are constant on a common interval. Then this path is, so here I have t, I have t, I have t, and this is t. Yes, this is better. Then g of t is geodesic. If and only if theta 1, theta 2, theta 3 are either decreasing or increasing. This is, I mean, each of theta 1 is either decreasing or increasing. This is a characterization of geodesics. It's better if I follow my notation here. Yes. Yes, tell me.
These are angles in a Euclidean triangle.
Yes.
Sum to pi.
Yes.
So how could they each of them?
No, one is decreasing, one is increasing. This is what I meant.
You said each of them is like.
Yes, I don't know how to formulate. This is why I changed, in fact. So how do you want to put it? So one can be decreasing and the two increasing and so on. This is why I said each. So theta 1 is either decreasing or increasing. Theta 2 is either increasing or decreasing, but not at the same time, of course. Yes, sure. Yes, sure. Yes. What? Yes, monotonic. Yes, you're right. You're right. If I put monotonic, it's better. Monotonic. Yes. No, it's not a parameterized geodesic. It's just a path whose length realizes the distance between the points. And I want to talk also about the Finsler structure. So the other day, Bankeshwar Tiwari explained to you what is a Finsler structure in this metric setting. So Finsler structure. So this is, if you heard the talk the other day, it's just a parameterized family of norms, parameterized of this space of triangles. A family of weak norms. Weak meaning that not necessarily symmetric in general, but here it will be symmetric, in fact. Parameterized by this space A, which you see you will consider as a family of norms of the tangent spaces. Okay, so for this, in fact, I have to parameterize my space. I have to take the following parameterization of my my space. So now I follow my notes. So I identify ATA with the following space, with the following surface in. So this is A1, A2, A3. So now I'm following my notes, okay? These are the lengths, these are the edge length, where A1 square plus A2 square minus A3 square is positive, A2 square plus A3 square minus A1 square is positive, and AT square plus A1 square minus A2 square is positive. So this is these are the parameters of my space, and then plus the condition that the area is A. And then in these parameters, the infinitesimal Finsler structure is okay, A1, A2, A3, V1, V2, V3. So this is the function on the tangent space, and this is the max of the norm of VI divided by AI. Yes, this is it. This is the infinitesimal Finsler structure. So and okay, so this is my first example. So this is the space of Euclidean triangles is equipped with Thurston metric, where I can prove at least 3 or 4 theorems on the geodesics, which I won't tell you here. There is there's an explicit description of the Finsler unit ball on each tangent space, and it's a hexagon. It's a hexagon whose shape the shape I mean whose yes, I mean the shape I mean the not only the shape as a whose isometry type matter is determined by the underlying point in the space, the underlying point. And then there's a theorem which tells you that if the two Finsler units balls are the same, then the points are the same. This is like the theorem which Kenichi told you the other day about Thurston's metric. So this is one thing. Let me say that maybe I want to say another property. No, it's not affine. This is what I said at the beginning. It's not affine. It's not affine. It's more complicated. And in the paper with Kenichi and Miyachi, we studied this map. We show that there are stable and unstable foliations and so on. It's something which you can study. Yes. It's not the affine map. Let me say that we tried a little bit the same thing for space of quadrilaterals instead of space of triangles, and we did not succeed, in fact, to prove anything interesting. So this is I think, a good problem for someone who wants to work on this. This same metric here, if you want to define it on the space of quadrilaterals in the plane, and then let me tell you a few things. Let me tell you a few things, in fact, about Euclidean surfaces. So I said quadrilaterals, but you have also other shapes. I mean, you can think of other shapes. I can, okay, this. Let's say I thought about this. So shapes like this, or you see, so my space is a space of rectangles with a semicircle attached. I think this is a very good example. You could think of semi-ellipse attached, but this is more complicated, I think. So just with this semi-discs attached. So you take two of these, this one here and this one here. And you ask questions about the best Lipschitz map. Does the best Lipschitz map necessarily map this rectangle to this rectangle and the disk to the disk or not? If you can answer this question, then you can, I think you can develop the theory for this space of shapes. And I want, yeah, I have some pictures there I want to show you for other kinds of shapes. Okay, so this was supposed to be the beginning of my talk. Let me just tell you. Let me just tell you about this paper here. So when you think of Teichmüller spaces of Euclidean surfaces, you think about Teichmüller space of the torus, right? So this was, as I said, 15 years ago, but I bring it back because with Ohshika and Miyachi, we did something more on this space very recently. So let me remind you of the Teichmüller space of the torus. Of course, this is equipped with Thurston's metric. So this is, I think, an interesting space. And let me tell you what is this metric. So it turns out, now I'm talking about this metric. When I talk about this metric, it means this one. So this metric, this is while Apollonian metric of the upper half plane and let me remind you, what is this Apollonian metric? Apollonian metric in fact, the term Apollonian comes because when you work with this metric, you end up dealing with circles, in fact, a lot of circles which appear. Families of circles. So the Apollonian metric is defined on the interior of a convex set by some formula. This is the formula now. This is convex set. You have X and you have Y. And you define the distance from X to Y as the supremum, of the distance between Y and A, X and A, where A is in the boundary of your convex set, and then you take the supremum over A. This is a metric which was studied more or less by people doing geometry. Some people, after we wrote this paper, somebody told me we should call it the Barbelian metric because it was studied by Barbelian. Anyway, so the result here is that the Teichmüller space of the torus equipped with Thurston's metric is the Barbelian, or did I put Apollonian metric of the upper half space, upper half plane. So I will not recall this because it would take all the rest of the hour. The Teichmüller, I mean, the Teichmüller space of the torus is equipped with the Teichmüller metric is the hyperbolic plane, right? I mean, some of you know this. So now, if I take the Thurston metric, I take the upper half part of the complex plane. I don't want to call it the upper half plane because it's not the hyperbolic plane. The upper half part of the complex plane equipped with this Apollonian metric, so X, Y, on. The same definition which are erased. And now the one important fact here, in fact, is that the arithmetic symmetrization. So let's call it here the Apollonian metric. Let's call it. I didn't give it a name. Let's call it zeta. Arithmetic symmetrization of zeta, that is 1/2 zeta of xy plus zeta of yx is the hyperbolic metric. So you can ask questions about the geodesics of this Thurston metric of the upper half plane, and it's a theorem, in fact, that the geodesics of this Apollonian metric of the upper half plane are the hyperbolic geodesics. So when I'm doing all this, you see, when I'm doing all this, I'm thinking of this table which Kenichi gave you in his first talk. He had a table where here you have, I think the Teichmüller setting, and here conformal setting or quasi-conformal, and here the hyperbolic setting. So here you have, of course, the Teichmüller metric, and here we are talking about the Thurston metric. So in the case of the torus, this is Apollonian, and this is the Teichmüller metric. So this is in the case of the torus. And they share the same geodesic. I think all the questions about the what happens for the symmetrization. In fact, we know. I mean, it's easy to see that the symmetrization of the Thurston metric in the case of a general surface, at least for the surfaces we study usually, the closed surfaces. Maybe for other surfaces it's different. The symmetrization of the Thurston metric is not the Teichmüller metric. So when I said maybe it happens for other surfaces, let me tell you what I mean. So what kind of hyperbolic surfaces? What kind of hyperbolic surfaces we did not study yet? So we studied closed surfaces. We studied finite type surfaces with boundary. We studied finite type surfaces with cusps. We studied finite type surfaces with funnels. We studied infinite type surfaces with cusps, funnel, and boundary, and so on and so on. I mean, there are results here and there on this question. Now, my question here, I started with the space of triangles in the Euclidean plane, and I asked the question for space of triangles in the hyperbolic plane. I will not give you all the questions which I think are interesting, but this is a question which tried to deal with, and the first things, I mean, the things we did on in the Euclidean case do not work at all. So here, one difference also is that this is three-dimensional. It's not two-dimensional as in the case of the torus. You don't have I mean, there's no meaning to, there's no necessity at all, and it's unnatural to take a fixed area, to take a space of triangles, a fixed area. So this is naturally a three-dimensional space. What is Thurston's metric in this space? Can you, I mean, you could define, you can define a metric, but you have to prove, theorems of this metric. For instance, you have to say what are the geodesics. You have to say what is the Finsler structure. In fact, the two or three things I told you, but there are many other things. So it's not impossible that here, for the Thurston metric, in this hyperbolic setting, I mean, I don't know whether the relation with the Thurston and the Teichmüller metric. Let me say a small thing. In fact, since Yorgos was talking about some predecessors, people who studied best Lipschitz maps, and I think the oldest date he gave is 1934, something like that. You wrote 1930. So I have a reference. In fact, I know this since a few years. A paper by Lavrentiev. So Mikhail Lavrentiev is one of the three persons who worked seriously with quasi-conformal maps. They are not the first. The first one is 19th century. But Lavrentiev and Grotsch and Teichmüller are the... So Lavrentiev has a paper on the type problem, asking whether you can how to find conditions necessary or sufficient for a surface to be parabolic or hyperbolic. That is, the universal cover of the surface, is it the complex plane or the disk? This is a very difficult problem, in fact, but he is the one who, and then he has, in one of these papers, he has a question, in fact. Of course, these people deal with the Riemann mapping theorem. And his question is about the distortion of the Riemann mapping theorem for a certain class of surfaces. He says, I don't know anything about the metric distortion of this map. You see, the Riemann mapping theorem sends you this disk to the round disk, and it preserves angles. But what can you say about the metric distortion of this map, the Lipschitz distortion? So all this is, okay, it's part of Higgs theory. I have only 10 minutes, and I want this guy to, yes? So I want to show something. So we finish with this, and I want to show you something else on Euclidean, on the Euclidean case. So this is something I talked about a lot, but I will skip. So this is on Milner's work on cartography, in fact. Yeah, I will not skip, but I want to say just a few words. So Milner has this problem of finding, okay, the distortion, the distortion of a geographical map. Now, the distortion is not the same definition as here, because in the cases we are considering, you see, we are the best Lipschitz map is realized, as several people said here, on a I mean, the best Lipschitz constant is realized on a laminate, but then you have a lot of flexibility on the rest of the surface. Okay, so when you have caught the essential, the place where the essential dynamics happens, then I mean it could be the identity on some parts of the surface. Okay, but in a geographical map, you want the map to be the least distortion, but the distortion must be equal on all the map, right? You want the distortion when you examine a geographical map. You want the distortion to be the same everywhere. If you can, because this is also not possible. It's from any theorem, from several theorems of spherical geometry. Several theorems tell you that you cannot have a constant distortion for a geographical map. So these are maps from the sphere to the plane. And this is a very old problem, in fact. Many mathematicians were interested in this. I will give you some hints later. But okay, so this is more or less, this more or less tells you that the map is Lipschitz. This tells you that the inverse of the map is Lipschitz, and sigma 1 and sigma 2 are the sigma 1 is the greatest constant which satisfies this. Sigma 2 is the smallest constant which satisfies this. And then the distortion is the logarithm of sigma 2 by sigma 1. This is the definition that, and we want, in geography, one wants to find maps F such that delta is as small as possible. Okay, so Milnor proves some theorem, and then he proves that for every set omega whose cardinality is greater than 3, there exists a minimal distortion map. But then he asks other questions. Is this map unique? Is it differentiable? Is it constructible? And what is the practical estimate of this distortion? And the response is unknown. Of course, this is what did I say? 1967, 1969. But let me say here, it's written here. In his collected works, in volume 1 of his collected works, Milnor makes some comment. This is recent. The collected works are recent, and he comments on his 1959 paper. And he says that all these problems are still open problems. And he has some conjectures. For instance, this one, for a distortion minimizing map is the minimum constant. Is the maximum scale minimized along the boundary? So he's thinking here of some kind of heat equation problem, and so on. So there are still several open problems other than this one. These, but others, in fact, for best distortion maps from the sphere to the plane. And now, okay, if I take instead of this definition of this is a definition which is very natural for cartographers, but I could take another definition, just like in Thurston, just one side of the distortion, and I can ask the same questions. Okay, so this is yeah, and this is, I mean, this is interesting because the only case where Milnor can prove this theorem, this existence theorem, with uniqueness, differentiability, and so on. The answer to the above question is positive in the case where omega is a spherical disk, so just a disk on the sphere. His domain is just a disk on the sphere. This is the simplest case you can think about. And here he has a formula for the distortion and so on, and he has no other cases which he can deal with. And then he gives the example. I mean, and it turns out that this construction of a geographical map was used by geographers since 300 years, in fact. And it is the one called azimuthal equidistance projection. It is the one which is on the flag of the United Nations, in fact. And so this is an instance where craftsmen here, these are geographers, constructed a map and then used it and so on, but without knowing, in fact, just intuitively, without knowing that this is the best map. And the first one who proved that this is the best map is Milner. So yes, so no, I would have liked to talk about Euler's work on map drawing. This is a map drawn by Euler, in fact. This is a map of the Russian Empire, and it uses. So you see, you have these foliations here, but these are the images of the meridians, and then the image of the parallels. The image of the parallels are these circles, and so this is a famous projection, which is called. Never mind. I don't want to speak a lot about the history. It's called the Delisle map. So when Euler was drawing maps, he was working under the direction of Joseph Nicolas Delisle, who was the main geographer at the Academy of Sciences. And interestingly, at the Russian Academy of Sciences, interestingly, there's a paper, a recent paper by Ohshika and Miyachi. They show that this Delisle map is the best among all sorts of geographical maps which share the same properties. For instance, sending meridians to lines intersecting in the same point, and the parallels to circles centered in this point. So I think this is another instance where geographers used a map, and then it was only recently that they proved, in fact, they proved that by any means, even quasi-conformally and by all sorts of distortions. Okay, so this is another thing. This is a paper. This is a book on geography. In fact, I became interested in geography after I worked on Thurston's best maps. In fact, you know, the word map. The word map invoked for me a geographical map. A geographical map is a beautiful object to look. So this is a map. This is a map, an ancient map from Ptolemy, and it's also constructed by the same, more or less the same principle as Euler's. Not exactly, but so I wanted to show you this because here you have India. In fact, here this is a map. This is a map from 1st century. So of course there are no maps of Ptolemy which survive. In fact, this is a map, I think, from 15th century, but it is drawn according to Ptolemy's. You know, Ptolemy has this book called the Geography. It consists of I think 5 chapters of theory, and then there are maybe 100 pages where he gives coordinates of cities, of islands, of small villages, of rivers and so on, just to be able to construct maps. So you take the coordinates of Ptolemy, and then you can build a map like this. And people did this since a long time. Okay, so I said I will. Yeah, okay. So now there's something I want to conclude with this. You see, there's this book by Darcy Thompson called On Growth and Form, first edition, 1917. And these things. In fact, I had heard about this book at various occasions. One of them is I was interested in. Okay, I don't have more. I was interested in, at some point I became interested in the work of René Thom, but from the philosophical point of view, I wrote a book on René Thom, it's in French. And Thom says that he learned a lot of things from this book, like he learned the idea of stratification. He learned the idea of stratification from this book. And this is about growth. You see, these are different shells. Nature follows the most economical path in principle. This is also a principle. And these are skulls of apes. And the people so you see, when I said, I asked you what is the best Lipschitz map from here to here? But you must take into account the stratification, in fact, which means here that you must send the eyes to the eye. You must send the I don't know in English how it's called this, and the teeth to the teeth, and so on and so on. I mean, what is the best map taking into account all this stratification? Let me also. I mentioned here John Milner in this setting also, because there's a lecture by Milner maybe 2 or 3 years ago, which he gave at the Institute for Advanced Study in Princeton about this book, in fact. And he says how much he is inspired from this book. And the lecture is on the internet. In fact, you can follow it. And I mentioned also to finish Thomas Lecuy. This is a new professor of biology at Collège de France in Paris, and this is the best position which any mathematician in France would dream to have, a professor at Collège de France. So this is the chair of biology, and this young Thomas Lecuy, his inaugural lecture, he gave it on this book. On growth and form. And the lectures are also on the internet. If you are interested, you can look. And in all his lectures, he mentioned this book. Anyway, for us, I think these pictures are very inspiring. And okay, this is what I wanted to say.
Questions?
Yes? Yeah, this is also a good question. The space of ideal, I mean polygons of a fixed number of vertices. Yeah, this is also a very good question. This was one question I tried, but I gave up. This is a very interesting space. Yes. I think it's open. For me, it's open, in fact. Yes.
Okay, let's thank Athanase again.
Okay.